This is for video lesson for chapter number 5. We are continuing the process of measuring heats of reaction. We call this calorimetry. The imagery part tells us we are measuring. Calorie is a measure of heat, and we use an piece of equipment called a calorimeter because it measures heat. Calorie is a unit of heat, just like joules and kilojoules are, although in chemistry we often refer to joules and kilojoules. Calorimeter, equipment used to measure the heat that's absorbed, endothermic, or released, exothermic, in a chemical reaction. So we can also find Q and deltaH from a calorimeter. For lab, when you watch the procedural lab video, me doing it, you're going to see that we have a coffee cup calorimeter where we have coffee cup, we have a lid, and then we have the thermometer. Now remember, the thermometer is measuring the temperature of the surroundings. It is not part of the reaction. So it is measuring what's going on only in the surroundings, because for these, the hardest part is to sign whether it is an endo, positive Q, or exo, negative Q reaction. So watch for that. It is a constant pressure calorimeter because it's taking place at atmospheric pressure. Also, we have a bomb calorimeter. We will not be using that, but it is not a constant pressure. And so we're going to start by working the first problem. There's a couple of assumptions we're going to see we have to take place, but we'll get to that. So for the first problem, a 100 ml portion of 0.5 molar HBr at a certain temperature is also added to KOH at the same temperature in the foam cup. This is much like what we did in lab when we added hydrochloric and sodium hydroxide. After mixing the two, the temperature, very important, rises. Now remember, the thermometer is measuring the surroundings. So I'm going to make that note. Thermometer measures what's going on in the surroundings. So in the surroundings, the temperature is increasing. So that should tell you something about what's happening. Is heat being lost by the system to the surroundings, or is heat being gained into the system? So because the thermometer is increasing in temperature, the surroundings are gaining heat. So if the surroundings are gaining heat, that means that the system is losing heat. So this tells us that regardless of what we calculate, that when we get the heat of the reaction, it better be negative, because the surroundings, remember that picture that we had where we have the reaction or system, and then the surroundings are in the outside, and our thermometer is right here. That means that heat in this case must be going from the reaction to the surroundings in order for the temperature to increase. All right, so that tells us it's exothermic. So we're going to jump back to our problem. And so we've got to figure out, how do we get the value? So we are either going to have to use Q is equal to M times S times delta T, or Q is equal to C delta T. Well, we're not given a heat capacity or specific heat capacity. So let's see what assumptions we have to make, because we're going to find out there are 4 assumptions we have to make in problems like this where we have a reaction taking place. And we know we have a reaction because we have hydrobromic acid reacting with potassium hydroxide, which is a known base. And so we could actually even come up with the products based on chapter 4. And so those products would be water and potassium bromide. So we already have a reaction. It's also balanced, and we need to find out what this delta H is. We already know it's negative, but we don't know what the number is. So our job, now that we have the equation, is to come up with what is that number. So when we go back to the 4 assumptions, let's look and see what it says. Assumption 1. The volumes of the solution are additive. All right, so we have 100 mils of hydrobromic and 100 mils of potassium hydroxide. So that means that if they're added based on assumption 1, that we have total volume of solution ends up being 200 mils. So this is assumption 1. We have to use these to solve the problem. We'll see how that all comes out. Assumption 2, the density and specific heat of the solution are the same as the water. Now, part of the reason that we can make that assumption is because the reaction is so dilute. So essentially it's saying that because it's relatively dilute, that it's the same as if it was just in water. So density and specific heat. What that means is that when we come here, assumption 2 tells me if we base it off that the density of the solution in this case, which is the same as the density of water, we found out in lab 1 was roughly 1 gram per mil. And the specific heat, when we look it up in the chart of water liquid, is equal to 4.184 joules per gram degree Celsius. Again, we're going to see how this works out. Assumption 3 is that no heat escapes. Now we know it's an experiment. Some heat's probably going to escape, but we're going to assume it's not. And then the last one is that all of the heat is transferred, whether it be in raising the temperature of the solution or raising the temperature of the surroundings. So let's come back to my problem. And when we look at the problem, let's see if we can come up with this. So now we know that we have a specific heat. It tells me that we've now got to use Q is equal to M times S times delta T. So again, we're looking for Q that we can ultimately adapt and find delta H. Mass of the solution, because now we have a solution of KOH and HBr. We use assumption 1 by using the volume of assumption 1, but again, we need mass units. So we're going to use assumption 2, indicating that the density of the solution is essentially the same as the density of water. That'll get us to mass of solution. Then the specific heat of the solution, we're assuming, is the same as the specific heat of water. Now, if you're given the specific heat of the solution that it's in, use that one. But in this case, we weren't given, so we know, therefore, we have to use these assumptions. And then delta T is final minus initial. Our final temperature was 23.65 minus 20.29. So Q for this reaction, once we do that calculation, is going to end up being 2811.7 joules. Because delta H is generally in kilojoules, I'm going to go ahead and convert that. So that'll be 2.8117 kilojoules. All right, now remember, the signs don't work out here. We already know that the sign for this has to be negative based on the fact that the temperature rises to 23.65. So we've already assigned the sign of the equation, or the sign of delta H, and we know it's to be exothermic. Now, because this is a stoichiometric relationship and we have a balanced equation, this, remember, delta H must be based on the balanced equation. It also, another thing that you are learning from this lesson is that in order to get from Q to a delta H that is based on a balanced equation, because we haven't had to do that before, in order to do that, we have to divide Q by the moles of the limiting reactant, which is why limiting reactants are important. That will get us to delta H. So this is a new equation for us. So to get from Q to delta H, a delta H for a balanced equation, we have to divide by the moles of limiting reactant. We haven't had to do that before because it's either been given to us or indirectly given to us. So that means we have to find the moles of the limiting reactant. To do that, we're going to take this information above, and we've got to find out which one of these limits the amount of either water or KBr produced. It doesn't matter which one we go to. So I'm going to start with 0.5. In fact, let me go ahead. I'm going to erase some of this information up top, so that way we can move it. And that way everybody I know can see it. So we'll change it to pink. So now we're finding moles of limiting reactant. And so we have 0.1 liter of HBr, and we're multiplying it by 0.5 molar. That's going to get me to 0.0500 moles of HBr. You can see from the stoichiometry in the balanced equation that for every 1 mole of HBr, there is 1 mole of water. And so we have 0.0500 moles of water produced from HBr. We would do the same with my potassium hydroxide. There's 0.1 liters. Multiply it by the concentration, which also happens to be 0.5 molar. We end up with 0.0500 moles of potassium hydroxide. And we go back to the stoichiometry. For every 1 mole of KOH, we have 1 mole of H20. And lo and behold, guess what? We have the same amount of H2O. So both, and you can have this, both KOH and both HBr in this specific reaction are limiting reactants. So it doesn't matter which one I choose. So in this last step, in order to get from Q to delta H, that means I'm going to take my 2.8117 kilojoules, and I'm going to divide it by the moles of my limiting reactant, which I just found were 0.500 moles, and that value is going to get me to my delta H. And for this, my delta H ends up being 56.2 kilojoules per mole. Now my delta H, this delta H now is based off of the stoichiometry of a balanced equation. So now I can plug that into my above equation. So I'll end up with delta H is equal to negative, because we already assigned that, 56.2 kilojoules per mole. And again, I can drop the mole because I know that it's based on the stoichiometry of this equation. These are the hardest of the hard because they have multiple concepts. Again, we had to use the Q divided by moles of limiting reactant because we had to have a delta H that's based on a balanced chemical equation. And I would work on some of those problems. It has a lot of multi-concepts from earlier chapters. So this is our final method of calculating delta H. Yay! And we're going to use standard enthalpies of formation, delta H's of F's. These come from tables. And essentially, the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. That's the verbatim definition. But ultimately, this is a heat of formation of a compound. And there's a chart for all of these. So water liquid will have a heat of formation. Water gas will have a heat of formation. Carbon dioxide will have a heat of formation. And ultimately, this, you'll notice, has a not value. That means that these elements are in their standard state. So when that heat of formation was calculated, it was done so at 1 atmosphere and 25 degrees Celsius, which is standard temperature and pressure. The delta H for a pure element in its standard state is 0 by definition. But again, you're going to have a chart, so you don't have to have that memorized. And so here is a chart, and you can see in the chart here, for example, is Br gas. Its delta H is 111.9 heat of formation in kilojoules per mole. Now to calculate the delta H of the reaction, this is the third equation and final one in the chapter, and that heat of reaction is equal to sigma, which means the sum of N, the coefficient of the reactant or product, times the products minus the sum of the coefficient times each reactant. So we're going to go through that, but this is the equation that you will use. So we've got a couple problems for this, and it tells us calculate deltaH for the combustion of 1 mole of propane, C3H8, and it gives us the heat of formation for propane. So the first thing we have to have is the equation. For all combustion reactions, it is the hydrocarbon in the presence of oxygen gas. And normally we would be given this. And the reactant or the products are always carbon dioxide and water. And phase is important. So on these, I normally will give you a little bit more information. You would probably already know that carbon dioxide and water are produced, but you might not know that the carbon dioxide is always going to be in the gas phase. And the water, depending on the amount of heat that's generated, will determine whether it's liquid or gas. And it looks like for this one, I have it in its liquid phase. So to find deltaH using deltaH finding these heats of formation, I would use that equation. So deltaH would equal, and I've got to make sure I have this balanced. So we got to balance the chemical equation. So I have 3 carbons, so I've got to have 3 carbon dioxides. I've got to have 8 hydrogens, so I do that. So then I got to figure out how many oxygens. Whew. So now I have a balanced equation. So I have deltaH is equal to, so we're going to go to the sum. So it's products minus reactants. I have 4 waters. So I have 4 times the heat of formation. That's what the N times the heat of formation of the products. Now this is going to be water liquid plus 3, that's the N, times the heat of formation of carbon dioxide gas, and those are my products, minus my reactants. My reactants is I've got 1 mole of the heat of formation of C3H8, and it's in the gaseous form, plus I've got 5 moles of the heat of formation of oxygen, and it's in the gas phase. Then we would go to our chart and we would find water liquid. So we're going to go back to that chart that we just saw and see if we can find water liquid on here. And you can see here's water liquid, and it would be negative 285.8. So we would have 4 times negative 285.8 kilojoules per mole, plus 3 times, we're going to go back to our chart and see if we can find carbon dioxide gas. There's my carbon dioxide gas, negative 393.5. So that's that half. Minus, we have 1. This wasn't given on our chart, negative 103.8 kilojoules per mole. Plus 5 times, and when we go to look at oxygen on our chart, you'll notice that oxygen gas is 0. Then we would sum all of that up, and we would end up with negative 2219.9 kilojoules. And that's how we would use that equation. So we have an exothermic reaction, and this is the deltaH for that overall. So we would use the chart and the stoichiometry to help us find that. Now there's a second problem, and it shows given the heat of deltaH of formation of magnesium hydroxide is negative 924.5 kilojoules per mole, calculate deltaH for the reaction of magnesium chloride with potassium hydroxide. So we've got to come up with products. So we know already that it's producing magnesium hydroxide solid, plus we know that we've got potassium chloride. Now the phase labels are going to come from what we learned in chapter 4. Everything we've done is based on water being in the solvent water. So we would go to our solubility chart and we would assign labels. So that's what you've got to do. So we would end up doing that and find that magnesium chloride is completely soluble, potassium hydroxide is completely soluble. Magnesium hydroxide is obviously a solid, and potassium chloride is completely soluble. Again, those come from the solubility chart, that information we learned in Chapter 4. We also have to have a balanced equation, so we would need to put 2's in front of the potassium hydroxide and the potassium chloride, and now it's balanced. So we still have to find delta H for this reaction. Here's what's interesting. If you go to the chart, which it doesn't have all of these, you're not going to see magnesium chloride aqueous because it doesn't exist like magnesium chloride because it's completely soluble. So what you're going to have to do is you're going to have to find the net ionic. So if you go to work a problem and you find out that you don't have these pieces, you can't find magnesium chloride aqueous, it's because you need a net ionic. So you would come up with your net ionic, which happens to be magnesium 2 plus aqueous plus 2 hydroxide aqueous yields magnesium hydroxide solid. Now you can use the chart and get the information that you need from the chart. So you can do your products minus your reactants. Now it gives you what the delta H is for this, but you could solve the rest of this problem. And ultimately, when you do that, you're going to find that delta H for this problem is 2.4 kilojoules. But I wanted you to see that if you end up with a reaction in which you can't find, say, for example, the heat of formation of magnesium chloride aqueous, it's because it doesn't exist like that, because it exists as ions. So you would need a net ionic. You can calculate that on your own and compare your result to 2.4. It should be close depending on what chart of delta H's you use, or H of formations. The last thing I want you to see in this chapter, and this is the end of Chapter 5, is this enthalpy diagram. It's an energy diagram. And notice, this is just time, if you will, on this axis. So this is as the reaction proceeds. In the first one, you'll notice the reactants start up top, and as we continue, the products are lower in energy. So remember, in that last equation, we just learned that delta H, based off the sum of those, is going to be the heats of formation products minus the heats of formation of the reactants. Now, this is a very simplified form, but if that's the case, note that the products are in a lower energy than the reactants. So that means that if we looked at this mathematically, we would have a negative delta H, so it would be exothermic. The products are lower in energy than the reactants. They are giving off energy as they move forward, so it's an exothermic reaction. In an endothermic, you see the opposite. You see that the reactants are here at a lower energy and the products that are a higher one, because as the reaction proceeds, those products are gaining energy or gaining heat, and so they're absorbing it, and they end up being endothermic. So you need to be able to look at some of these graphs and also determine exo versus endo. If you looked at it just mathematically, again, this is a very simplified version, but products minus reactants, you would have a larger number minus a smaller number, and you would end up with a positive delta H, or thereby endothermic. Make sure you review this material, work some problems, and be ready for class on Tuesday.